And we are live. I'm going to kick off the countdown timer. We're going to start in 30 seconds. All right, what's going on, everybody? Welcome to another live episode. We got my brother Mark back on. What's going on, Mark?
Hey guys, just happy to be here. Looking forward to it.
I like that.
Yeah,
I like the energy.
Yeah.
So we're excited to have another live workshop with everybody. This is something that we would like to continue to do for those in our FE and our PE groups and course members. What happens is we end up going live on this stuff, and then we'll keep this up for a few days, and then it will be taken down on our channels and be put into our courses. And so with that, I want to make sure if you are jumping on live with us and you're not a member of our course, go to civilengineeringacademy.com and go check out the courses that we do offer. We have an FE course. Mark is a big instructor in there. We got a PE course, and we also have depth review courses for those specific for the PE exam. So lots of material for people, lots of stuff going on, and we want to make sure you're prepared for your exams. That's exam day.
That's the goal.
So anyway, with that, I'm going to turn the time over to Mark so we can get rolling. Today we're going to be talking about transportation topics, and Mark's prepared some based on some feedback that we've had. And feel free to be active in the comments. We can get to your questions there, and a lot of type stuff that maybe even theory stuff. We could just talk about it openly and just kind of get it out of the way. So anyway, I will be monitoring the chats, and Mark will be on here, and I'll give him a pause whenever we get questions. But with that, I'll turn it over to you, Mark, and you can get rolling.
Right on. So what we're going to do here is we'll share my screen so you can see me working these problems. But we're going to work 5 problems today. We're going to have a couple that I would say are more of the breadth section, or maybe more of the simpler FE type questions that deal with traffic parameters, traffic volume, highway capacity type problems, stuff that you'd find in the highway capacity manual, which, by the way, should be one of your main references for your transportation type problems. You want to make sure you've got the most recent highway capacity manual. I think the 6th edition is current, but I believe a 7th edition is shortly coming out. Anyway, we're going to look at 2 problems that are kind of quick hitters. We're going to look at a 3rd problem that's probably more of a depth type problem for highway capacity. And then we're going to get into some, I guess what we'd call geomatics. So we're going to look at some vertical curve type problems, some horizontal curve type problems, a couple of those, which tend to come from your AASHTO Green book as a reference. And so with that, I am going to share my screen here, and hopefully everybody can see that. Is everybody seeing my screen?
Isaac, let me add it to the stream, Mark, and we now they got it.
All right.
Again, do you want to answer some of these just kind of theory or maybe opinion questions coming up?
Okay. What do we got?
One of them is from Mo. Let me see if I can display this. It says, I am currently in a project with NYSDOT. They are thinking of replacing loops against cameras. Can we discuss that too? Traffic signal loop cost, maintenance versus 360 camera installation.
Okay, it sounds like Mo's getting into something that's called ATMS. That is a specific question that I don't think intelligently respond to that. If you're looking at costs, I work for a company that does a lot of ATMS, so it's the traffic control systems, the automatic traffic maintenance systems that get installed into intersections. They're the cameras, the loops that he's talking about, the inductive loops that they set into the lanes that monitor the traffic flow and the volumes, and then adjust traffic control, traffic light timings, phasings, and the like. But I would have to go back and look at specific costs of those things, and make some comparisons to talk intelligently about that.
Sounds
I don't know
good.
that I'm prepared to do that right now.
How about your opinion on this from Caramelino? Sorry, I probably slaughtered that. Should talk about the problem of expensive construction in the U.S. in terms of cost per mile when building tracks compared to European and Asian countries.
That's an interesting question. So when we look at the company that I work for, when we're looking at DOT work, we typically do a lot of work with UDOT. I'm in Utah, and UDOT, they fancy themselves as kind of one of the more progressive DOTs, and they do things like design build, a lot of GC type delivery methods that they feel like helps drive down the costs. And I think they've had a lot of success doing that, specifically with design build delivery, mainly because it gets the general contractor involved in the design work. So the parameters for the project are issued, general parameters, and then the specific design is left up to the general contractor, who teams up with a transportation engineer. And those two come up with the actual design, and they have the freedom to economize everything that they need. Some of the things that add costs. Sometimes you get into MSE walls and embankments and approaches that get too steep that add costs. And so they're able to look at, elevations, and I'm just giving an example, and maybe able to reduce the costs of embankments and MSE walls, and it depends on the alignment, but they're given the freedom to basically make the design as cheap as possible. And so they come up with the design, and they propose on the project, and UDOT selects a winning contractor based on not only their price, their projected cost for the project, but their overall design and how efficient it is and how well it's done. And so by doing that, they get nice projects completed for the state, for the traveling public, and the costs get lowered. So and I don't think all of the DOTs around the nation have embraced alternate delivery methods. So I would say that's a big, that's something that could help, the cost per mile go down if more DOTs would embrace that philosophy, that design build.
Sounds good. Let's get to your problems.
All right, so let's get to these problems. So these are. This first one says, during a peak travel period, 7 a.m. to 8:30 a.m., the local public transit agency runs a total of 10 buses. The first bus arrives at a critical stop at 7 a.m., and the last bus arrives for passengers at 8:30 a.m. The bus headway is most nearly what? Now, through our problems here, I'm going to be referring to different formulas that are going to appear like they just come out of thin air, but most of them are coming from, your highway capacity manual, the current edition. They're coming from your AASHTO Green Book. It's important that you get up-to-date reference material, and all of this, all these formulas that I'm going to be throwing at you, all of the tables that I'm going to be throwing at you. Those are all available in those references. Some of these are also available in, say, like the FE reference handbook. And so when I throw out an equation or a definition, it's usually coming from one of those reference manuals. So I'm going to do it again here when I say that headway equals the total time divided by n minus 1 intervals, okay? And headway is defined as the time interval between consecutive vehicles. And so if we were to imagine what's going on here, here's a bus. Here's a stop sign. And there's 10 buses that are going around in a loop, stopping at a stop sign to pick up passengers. And the headway is the time interval between consecutive vehicles. So if this was bus 1, and then down the road, we had a bus 2, the headway is kind of the time interval, and I'll label that as a T here, between the two buses arriving at the same stop. Okay, that's what's defined as the headway. So for this one, we could say that our headway, and it's n minus 1, because the assumption is that bus number 1 is already at the stop, and bus 2 is the next one to line up. So the first interval that you're counting is this interval right through here, right? I'll call that I. Okay. So headway is just going to equal the total time. So from 7 a.m. to 8:30 is just 90 minutes. And we're going to divide that by the 10 buses minus 1. And pretty straightforward. We get 10 minutes. Okay. So that's headway. It's just a fancy name of describing the time interval again between consecutive vehicles. In this case, bus. Okay. Is there any questions out there on this one, Isaac?
Any questions? No, nothing's come in. So I think this one's pretty straightforward.
Yeah,
Mark.
pretty easy. Let's go to the next one here. Problem 2. So this one says a 4-lane highway has 2 lanes in each direction. If it is known that the saturation headway is 1.9 seconds per vehicle lane, what is the capacity per lane of freeway? So this one, again, is dealing with headway, but this is a different headway. This is the saturation headway. And so, again, this is another term that's defined in our reference material, but we can say that the saturation headway is 360 seconds per hour divided by the actual headway, which we're just going to call H, and those units are seconds per vehicle per lane. Okay. So in the problem, we are given an actual headway of 1.9 seconds. And so our saturation headway, again, this is per our highway capacity manual. We're using that for our reference material here. We can just get at this really quick. So 360 seconds per hour divided by our actual headway of 1.9 seconds per vehicle per lane. And we're just going to come up really quick with 1,895 vehicle per hour per lane. And that is our saturation headway. Again, pretty straightforward. But it helps define these terms that pop up on these breadth type questions that you might get. Okay. Any questions with that one? Pretty straightforward.
Any questions about this? Capacity per lane of freeway. Anything about terms? Anything? If you guys have any questions, feel free to be active in the chat room. But right now, Mark, nothing. If we get one, I'll come back to it.
Okay. This one's a little more involved. This one's a little more in depth. This is a classic kind of highway capacity problem that you kind of want to get a feel for, because most likely you'll encounter something similar in a testing situation. This one says a 6-lane, 3 lanes in each direction highway passes through level terrain in an urban area. The highway is built with 11-foot wide lanes and barrier 2 foot from the outer pavement edges of both slow lanes, which are the farthest right side lanes. The one direction peak hourly volume during the weekday commute is 2,700 vehicles per hour. Traffic consists of 3% buses and 5% trucks. Interchanges occur once per mile. Peak hour factor is 0.9, and the posted speed limit is 65 miles an hour. And the base free flow speed is 70 miles an hour. And then we've got a series of 4 questions that we need to answer that we'll progressively go through. So first, what is the passenger car equivalent flow rate per lane? What is the speed during peak hour travel, or the FFS, which is the free flow speed? There's another name for that. What is the density, and what is the LOS, or level of service? And again, I've pre-populated with all of the charts that we need, that again are all available in your highway capacity manual. And these are taken from the 6th edition, and we'll be consulting these charts as we go through the calculations. But first thing we need to do is determine what the what we need to determine what the heavy vehicle factor is. So we've got traffic. It's primarily passenger cars, but we're trying to make sure that the trucks and the buses or any RVs are converted to passenger car equivalents, so that we can run it through our equations here. So for the first part, what is the passenger car equivalent flow rate per lane? We've got to factor in these trucks and these buses into the overall traffic flow. And so if I look here at my table, and again, this is coming from the highway capacity manual. If I look at my passenger car equivalents, in the problem statement, it says that we're passing through level terrain. So if I look at my chart here, I've got my terrain. Here's my level terrain, and it's in an urban area. That's nice to know, but not necessarily pertinent. And I've given the truck and buses for my E sub T factor, which is passenger car equivalent for trucks, of 1.5. Okay, so I'm going to use that. I've got another factor here for RVs that's nice to know, but they didn't mention any RVs specifically in the problem statement. They've just told me I've got 3% buses and 5% trucks. So I'm trying to get those buses and trucks converted into passenger car equivalents. And so to do that, I need to know what is called the heavy vehicle factor. So we're going to call this F sub HV, and that equals 1 divided by 1 plus P sub T, and that's your percent truck traffic times your E sub T, which is our equivalent truck factor from the table, minus 1 plus your P sub R, which is your RV factor, which we don't have any RVs in our problem, but this is the equation that you'd find in your highway capacity manual to calculate your heavy vehicle factor. So we can take this out of the equation because we know that goes to 0 because we don't have any RVs. So we're going to say our FHV. Oh, and I need to do one more thing. So our P sub T, again, is the percent truck traffic. And what we're going to do is we're going to say that even though we're buses and trucks involved in this traffic flow, we're going to say that because the chart combines trucks and buses, that essentially they're going to be the same type. They're going to be categorized as the same type of traffic. Okay, so we're going to say our truck traffic is just the two combined. We're just going to say it's 0.03 plus 0.05. So our P sub T, or our percent of truck traffic, is just going to be those two combined. It's going to be 0.08. Okay. So our heavy vehicle factor is going to be 1 divided by 1 plus 0.08 times 1.5, which we got from the chart. Our E sub T factor, our equivalent traffic factor, minus 1. And again, I could put this plus 0, but we determined there wasn't any RVs. So that goes away. And we should come out with a 0.962 for our heavy vehicle factor. Okay. Now, again, from our highway capacity manual, we're going to find out that we can say that our flow rate, our V, is going to be our V sub P, which is our demand flow rate, times our peak hour factor, which we'll define here in a little bit, times N, which is the number of lanes that we're dealing with, times our heavy vehicle factor, which we just calculate, times our F sub P, which is an interesting factor. This one's a driver population factor. Okay. And we're essentially, for this first part of this problem, we're trying to find, again, the passenger car equivalent flow rate per lane. And that is the same as our V sub P, which is our demand flow rate per lane, this value here. So we need to solve for that, okay? We can do that pretty easy. I won't go through all of the iterations on how to rearrange this. You guys, I'm assuming, know algebra. So we're going to say that's the peak hour factor times the number of lanes times the heavy vehicle factor times the population factor. Okay, so let's figure out what those are. Let's solve for this thing. So V sub P, so we know our flow rate, right? That was given to us in the problem statement. We've got 2,700 vehicles per hour, and our peak hour rate, or peak hour factor, excuse me, was given to us as 0.9. So we've got that. And our number of lanes in each direction was 3, right? We calculate our heavy vehicle factor at 0.962. And then our F sub P, now this factor is kind of, it's a little bit arbitrary. We can assume that the local population knows the terrain, they know the route on this commute. The population is well acquainted with the route. And so we're going to say that the F sub P is just 1.0. If we could rationalize that maybe they didn't know the route all that well, that maybe, I don't know, you had maybe this was a road in Hawaii and you could factor in maybe a percentage of tourists that were driving down the road, people that didn't know where they were going. You might want to adjust that factor down. But we're going to assume that everybody knows where they're going. So our V sub P, if we calculate that out, we should get 1040 passenger cars per hour per lane. Okay? So that's the answer to the first part of our question. Now, let's look at figuring out what the speed during peak hour travel is, or our free flow speed. Okay. We were, again, we can look up what the free flow speed is in our reference material. And it's going to equal, free flow speed equals the BFFS. Okay. Which is the actual, it's the base free flow speed. And then it's minus the free flow speed is the base free flow speed minus these factors. So we've got an FLW minus an FRLC minus, and you'll find out the more traffic engineering stuff that you do that a lot of the equations are very empirical based on observation. You can see that here with this equation as TRD is raised to the 0.84, which is kind of interesting. But TRD is the total ramp or interchange density. And we've got the factor FRLC, which is the right side clearance factor on the lane. And then we've got FLW, which let's see, that's the traffic, the average lane width. It's the lane width factor. That's what that is. So those, again, are just their table lookups, right? So we were given the BFF. Let's see, FFS equals the BFFS, which I need to erase that because we know what that is. We look up into the problem statement. It tells us that the posted speed limit was 65, but the base free flow speed is 70. Okay, so we know that the BFFS is 70. Okay, and then we're going to figure out what these other factors are. Well, if we go to the FLW table, we can look at our lane width. We were told that our lanes are going to be at 11 feet, so we can look right here. And between 11 and 12, our FLW, our lane width factor is 1.9. And then our FRLC factor, right, for clearance on our lanes. So we've got 3 lanes in one direction. We were told in the problem statement that we had 2 feet of clearance on the right side. So that's going to be a 1.6 factor. So 1.9. 1.9 minus your 1.6 minus your 3.22 times your TRD, which was your ramp density. I think we were told in the problem statement that we had 1 ramp per mile or 1 interchange per mile. So TRD is 1, and all that's raised to the 0.84. Okay, so we go through that calculation. You should come up with 63.28 miles per hour, and we'll go ahead and round that down to just 63 mph. Okay, so there's our free flow speed. Now let's look at the next part of our calculation. We were asked to calculate the density. And again, this is more of a depth problem that you might have on a test. So the density, again, consulting your reference material that you've got, the density is your V sub P divided by your S, which is the same thing as your V sub P divided by your free flow speed. So we have all those values, right? We've calculated those previously. So we can say 1040, and that's passenger cars per hour per lane, all divided by our 63 miles per hour that we just calculated. And we've got a density now, if you grind through that, of 16.5 passenger cars per mile per mile per lane. Okay. And then finally, last but not least, we're asked, what is the level of service per the highway capacity manual? Well, we've got this chart right here that I've extracted from the highway capacity manual, and it says that if we've got a density of less than 11, then we're at level of service A. If we're between 11 and 18, we're at B. 18 to 26, C, D, E, F. You can read down the line there. At 16.5, we are right on line here. We are between 11 and 18. So our LOS, level of service, equals B. So, kind of a lengthy highway capacity problem, but it kind of walks you through several highway capacity parameters that might be common on a test. And
I would say any one of these could. I mean, I've seen that level of service one come up on the breadth exam as a theory question.
And another thing, that level of service, municipalities love this measurement. They, if anybody's done any work for a municipality and maybe you're changing an intersection or maybe you're a developer and you're putting in a department store and they're worried about the traffic load on their streets. They're always worried about, well, what's going to be the level of service after the development's in, and that's a big number for municipalities a lot of times.
Right. A couple questions that came up. Let's see here. Can you comment on how to locate all of these equations in the HCM? There was also one about how to navigate the HCM. Any tips around that?
Short of using the index, no.
Tab it up well.
Just tab it up. I mean, get in your index and look up these terms. Obviously, everything's going to be categorized by free flow speed, basic free flow speed, and these factors. And just index it up and put tabs on those locations where it specifically has these tables listed is what I would do. But a lot of these things are summarized in other reference material. Like I say, like the FE, handbook has a lot of these things.
Even the
you just want to be ready with. Go ahead.
Oh, I was just saying, even the civil engineering reference manual has a lot of these things in there as well.
Yes, the CERM has all this stuff as well, and that's. If you don't want to go looking around everywhere for these specific tables, some of those, I'll call them overall references, like the CERM, like the FE. I mean, those are good sources too. Just make sure that in a testing situation, if you have, so on the FE, all you're allowed is, of course, is the FE handbook. That's all the material you're allowed, and so you want to know where stuff is in there. But for a PE, or another testing situation where you're allowed reference material, maybe you're tabbing up your CERM or whatever you're using, for the test. So you've got it all available.
Here's another question from Mo. How can we know if a problem is a multi-lane highway or freeway?
Well, all that matters is that you're defining the number of lanes in each direction. It doesn't matter if it's a highway or a freeway. So if we have, let's say, if I go up here, so if I go back up here to the top, all that matters is that we know the terrain, and that's a relative comparison. Is it level, rolling, or mountainous? And then the number of lanes that we've got in each direction. I don't know that it matters that we're defining whether it's a highway, which implies that it's elevated right off the main, surface of whatever community that the roadway is passing through. A highway just means it's elevated. Freeway just means it's probably at the surface, but the flow of traffic doesn't care if you're elevated or if you're at the surface, right? We just care how many lanes of traffic we got and how many what the terrain is like.
Perfect. I think that's all we got. Let's see. Tucker says the CERM has it with the table numbers and equation numbers listed.
Perfect.
There you go.
There's confirmation on what we talked about.
Okay,
Okay,
any
cool.
questions surrounding this one?
Okay, we're
Level
gonna,
of service, density, peak hour travel.
yeah, those are other parameters we could talk about. Do we want to bring those in now? I guess we can. We had some questions about, average daily traffic and average annual daily traffic and K factors and some of those things. Those are all volume parameters. And those are all things that municipalities and governing agencies use to measure how much traffic's going across their thoroughfares and their main traffic ways. But that's something that you're essentially counting up cars during a time interval and then determining some of these measurements. They're basically on the spot type measurements and calculations. But did you want to go through some of those things? Is that
No, that's okay. I was just reviewing part of A, B, C, and D here. We've talked about level of service. We've talked about density.
Yeah, and if you're looking at annual average daily traffic or average daily traffic or even design hourly volume and K factors and those things, a good reference, it's kind of a little quick reference, is the FHWA, the Federal Highway Administration, issues a little, they call it the Traffic Data Computational Method Pocket Guide. And it's a PL 18027 if you want to know the exact reference number for that book. And it specifically gets into how to calculate ADT, AADT, and DHV. And essentially, they're different averages for counting up cars that are traveling across the thoroughfare or a street, and coming up with these measurements. But I could put those calculations down, but I would just reference anybody who's worried about those things specifically to look at that. And it's also specifically addressed in your CERM or whatever your study material is that you're using. But
Okay.
they're fairly basic calculations. It's all, I don't know if I'd go so far as to call it maybe stochastic. I guess it's still based on a statistical, you're still counting cars, but you're just counting cars during certain time intervals and coming up with these averages.
Very good.
Different streets.
Tucker also says the PPI Transportation Depth Book has actual tables and equations. I think it's the same that Mo just mentioned. So,
okay.
Yeah, if you dive into some of the other resources that are out there, a lot of them will point those tables right out in the reference guide. If anybody does need that from PPI, you can use our link at civilengineeringacademy.com/PPI, and you can use the code CIVAC and get 15% off if you still need that. I'll leave a link here in the comments.
Okay, cool, man. Let's head into problem number 4. So now we're going to kind of get away from the highway capacity type problems. We're going to get into some vertical and horizontal curve stuff. So let's look at a vertical curve first. This one says, if an SSD or a stopping site distance of 550 feet is to be provided on a sag vertical curve with tangent grades of -3% and 1%, what should the length of the curve be under standard headlight criteria? And that's kind of an AASHTO term that you'll see in some of their typical formulas, their empirical formulas that they derive. And we'll talk about that. But first thing I wanted to do is look at the anatomy of a vertical curve. So before we get into this, so this one would be I'll put the label up here. This one is a crest curve, right? Because it's got a peak right here at the top. And this one would be our sag curve. So the two types of vertical curves. Now, just a quick overview of some of the terms. So the BVC is the beginning of the vertical curve. The EVC is the end of the curve. We've got this turning point that's right here. This is basically where the slope of the curve is supposed to be 0, right? So if you remember back to your calculus courses, whenever you could calculate the slope on a curve at 0, you knew you had an inflection point. And that's what they're talking about with this turning point, where the derivative of the curve is 0 or the slope is 0. That's this turning point when the crest changes direction, essentially switches from a positive to a negative slope is another way of looking at it. And a sag curve has the same thing. It's got a turning point right there where the slope equals 0. The vertex is V right here at the tip where the tangent points kind of converge.
Hey, Mark, let's get the mic closer to your mouth. We lost you there for a second.
Oh, how about now?
That's better.
All right. So we're just going over, hopefully everybody can see my crest and sag curves here. We're just going over the terms. M is the middle ordinate, or it's the distance from the center line of the lane to the vertex. And that's something that we'll use on a horizontal curve problem on the next one, but we'll talk about that later. And then, of course, G1 and G2 are just the approach grades. And L is the length of the curve from BVC to EVC. And then X is just a possible, it's the distance from BVC to the turning point is what the X is. So just a quick review of the anatomy, I'll call it, of the vertical curve. And so let's get back to our problem. So we've got 550 feet is to be provided as stopping sight distance. So, and we're dealing with a sag curve, right? So if you can visualize, here's our sag curve. And we're supposed to be providing a stopping sight distance. So if you could imagine, a little car right here. Maybe that's more of a bus. Anyway, he's cruising down this sag curve, and he's got a certain sight distance that he can see up ahead, and that's kind of dictated by how the measurements and the dimensions of this sag curve. And so we need a stopping sight distance of 550 feet on this sag curve. And our grades we've been given on our minus side is -3, right? And then over here is a 1%. And we're supposed to find the length of the curve under the standard headlight criteria. So if the headlights are just shining straight down, right? If it's dark, this bus, if that's what we're going to call it, let's say there's a guy standing here. Here's an obstacle. If he's got his headlights shining down, he needs to have this distance figured out, or this curve needs to be optimized so that the headlights will alert this driver that there's somebody in the way, right? So that's what the standard headlight criteria is. It's just, if you've got a straight beam of light, what's that distance that the driver can view the obstacle and be able to stop in time, the stopping sight distance, and avoid that obstacle, okay? And so if we look down here at our chart, and this one again is coming from the Green Book, the AASHTO Green Book. If we assume that our sight distance is larger than our curve length, which is what we're going to assume here, then if we've got a sag vertical curve and it's based on headlight criteria, this is going to be the required length of the curve, the formula for the required length. Okay, L equals 2 times S minus 400 plus 3.5S, all divided by A. Okay, so let's just plug and chug here. We can say that L equals 2 times S minus 400 plus 3.5s all divided by A. So L is the length of the curve. A is the absolute value of the algebraic difference in the grades. So we'll calculate that. And then S is the stopping sight distance. So we can say that our S was given to us as 550 feet. Our A is going to equal 1 minus a minus 3. And then we're going to take the absolute value of that number. So if we go through that, we're going to come up with 4% on our A. And so our final length of curve is going to equal 2 times 550 feet minus 400 plus 3.5 times 550, all divided by 3. All divided by 4. Okay. So if we look at that calculation real quick, and I realize that I had that plugged in wrong, so I'm going through this by hand real quick.
Live.
But I'm using my calculator here. And if I go through this, divide it by 4, subtract, here we go. We're going to come up with 518.7. So we'll say 519 feet. So that curve for the L, the length of the curve needs to be 519 feet for this this driver to be able to see that obstacle in the road in time to stop and avoid the obstacle. Okay.
Question came up. The A value is not 0.04 since it is a difference of grade? Question mark.
Yeah, and this is one of those weird empirical things that you just kind of have to look at the formula and see what's required. So, yeah, even though technically when you're dealing with percentages, if this could be 0.01 minus a minus 0.03 like this, but for this formula, you're using whole numbers for percentages.
Yeah, keep it as a whole number or work in all decimals, right? It's like one or the other.
Yeah.
Transportation.
Yeah. And it's just because of the empirical nature of the equation that we're working with.
Another question that came up is, why did you decide S is greater than L?
Because that is the standard assumption that you go in with. And we can verify that as soon as we go through the calculation. We've already verified that, right? We've calculated that our L is 519, and we were told at the beginning that our S was 550, right? So even though I arbitrarily picked that at the first, I've just verified that that's true because my L is 519, right? So I've just verified that my S is greater than my L with that number right there.
Now, if that wasn't, you would go back and use the other equation.
That's right. Then you'd go back and you'd use this bad boy right here.
So that's one of the things you're just going to have to make an assumption on, figure it out, and then see how it shakes out.
Yeah, and I'd say the majority of the time this is what applies, but you could go the other way, but then you'd find out, oh, crap, I'm short. And then you'd have to redo this one. So, yeah, that's a good point.
Short. Okay.
I'm short.
Any other questions on this guy? Got a thumbs up from Emil. Appreciate that.
Okay. Let's head into the last one here. So this one will be a horizontal curve type problem. And it reads like this. It says for a horizontal curve with a radius of 5,150 feet, the stopping sight distance, SSD, is 1,980 feet. What is most nearly the horizontal sightline offset, or HSO, wherein no visual obstruction is allowed? And so, again, I've drawn a picture of what's going on with this problem. Hopefully that's legible enough. My artistic skills aren't the best in the world, but
Looks
I
good.
wanted again. What's that?
I think it looks good.
Thanks, Isaac. That's nice of you. But I want to go through again the anatomy of a horizontal curve, just so everybody's kind of on the same page. So we got a little bit different labeling on a horizontal curve. Again, we're still labeling a curve, but PC is the point of curvature, right? That's what that point is. The PT is the point of tangent. It's where the curve ends. We've got the chord, that's the line passing through the 2 points. Here's the actual curve going around here. That L is the length of the curve. I is the intersection angle. This M is the middle ordinate, but it's also sometimes called the HSO, right? So in the problem, when they're asking for the horizontal sightline offset, they're basically asking for that M dimension. Just like the vertical curve, we've got our radius here. We've got our origin. Again, I is the intersection angle. E is the internal distance from the vertex to the midpoint of the curve. And you can kind of look across there, and here's the back tangent line, the forward tangent line. T is actually the distance between PI, which is the point of intersection on the tangent lines. It's pretty much everything sliced and diced. Every measurement along that curve is you can dream of has been provided. Okay. So with that in mind, we're going to look at our problem. And here we've got again, a little graphic that describes what's going on. So here's a car passing along a highway. He's got a stopping sight distance of the amount of the distance along the curve to the object on the road. So if we were to say, here's a little guy, he's the object on the road. This car has a line of sight, and if you were to imagine maybe this obstacle is a tree on the road that he can't see around till he drives around that point, this M distance, or the HSO distance, the horizontal sightline offset distance, is critical, right? For this car to have enough distance to stop before he hits this guy or this object on the road, he's got to have enough distance between the top of this tree or whatever our obstruction is to be able to see that guy and then have enough stopping distance to not hit him. Okay. So that's what we're calculating is this HSO distance from the top of the tree to the middle of the lane of the road, the car's travel path before he hits this guy. So again, we're going to assume that our SSD, or our stopping distance, is going to be less than the curve length. And if that's true, then we can say that our HSO, or we could say our M, if we want to make direct correlation to a standard horizontal curve layout, it's going to be R. And again, I'm getting this from the table right here. So I've got sight distance to see around an obstruction, and my HSO, right, equals R times 1 minus cosine of 28.65 S over R. That's what I'm using. And again, I got this from standard reference material. This one is specifically from the Ashto Green Book, is where this one's derived or taken from. So 1 minus cosine of 28.65 S all over R. Okay, so now it's just a plug and chug type problem now. So we've got 51 50. Right, that's our radius times 1 minus the cosine of 28.65 times 1980. And that's all divided by our radius, which was 5150. Put a bracket around that one and then another bracket. And you should come up with 94.9 feet, which I would probably just say that's close enough to 95 feet. And that's your answer. So what we're saying is this distance from center of lane, to the top of the obstacle, that distance right there, that arrow should be at the center of the lane. That's your 95 feet. And if they can maintain that, and if you are designing the alignment on this road, and say this obstruction was a tree, some maybe environmentally sensitive type obstruction, you might have to shift the whole curve of the road up just so you could avoid this obstruction and give the driver a adequate line of sight and stopping distance to avoid the object on the road. So pretty straightforward in the calculation. It's just kind of understanding the overall concept and then making sure that you're looking up the appropriate reference material for your formula, and bam, you got it.
Sweet.
So here we are.
Got any comments? Any questions? Comments? Issues? No, it's Saturday.
It's Saturday, exactly. Anyway, that's it. Hopefully that helps some people understand at least a couple basic concepts. But yeah, those are good problems. There's all kinds of as you know, vertical and horizontal curve type problems that are out there that you have to work. But for me, it helps to start with, I call it the anatomy of the curve before I get going. And then based on the problem statement, just try to understand what's being asked based on the anatomy of the curve, and then trying to find the appropriate formulas to apply. And you can usually get at the answer pretty straightforward on these horizontal and vertical curves. You just got to kind of get your head around the concept that's being presented there.
Cool. Any questions out there regarding horizontal curves? Haven't seen any come in.
Okay.
And I think that's your last problem, isn't it, Mark?
That is it, my friends.
Okay. We'll jump to this. Hey, we are hitting here about 1 hour, and we want to make sure you guys do have a good Saturday, and it's not just filled with
studying
problems.
Yeah, that would be not very fun.
Thanks, Mark, for running that. If you guys have additional problems, feel free to email me, Isaac at Civil Engineering Academy. That's ISAAC. We will plan to do some live sessions in the future as we get some problems related to that. One was requested to do geotech, so I'll look at trying to prepare something.
Yeah, that'll be a fun one.
But yeah, so if any of you guys still need a course or need additional material, go check out our courses. You can go to civilengineeringacademy.com and check out our FE, PE, or depth courses, all there. And we have tons of problems there, additional problems you can go check out. So,
right on.
Mark, any last parting words?
Thanks for the fun. Once again, Isaac, it was a good time.
All right, everybody. Good luck.
Those are my parting words.
All right.
Yes, and good luck to everybody on their exams and their studying.
Yeah. Keep in touch. Let us know how it goes, but we'll keep doing these. Thanks, everybody.
Okay. Thanks, guys.
Bye.